So this was the so-called Eustace project, where we had lots of project partners throughout the EU. We had 3 Met Offices. I don't know what the plural of sort of a collective of Met Offices. University of Leicester, Reading, the STFC, the University of Bath, because I was there when the project started. Now I'm at the University of Edinburgh, and then we had the University of Bern in Switzerland. And we had this ambitious goal of reconstructing global temperature since 1850 on a daily basis. And, well, it's quite ambitious to try to do that. So we also had to be pragmatic. So what I'm going to mostly present the sort of the ambitious, or parts of the ambitious things, and then show how the pragmatic thing turned out in the end. So what we want to do is to take all the data we could lay our hands on that was useful, which is mostly weather stations when you go back in time, and also data from ships, and more recently from satellites of various types. And why do you need so many different Met Offices involved in a project like this? And that is because different people know about different kinds of things. So the UK Met Office, they work a lot on ocean data. The Danish Met Office works a lot on ice. So anything to do with ice, then you talk to the people in Copenhagen, because they know all about ice. So the idea was to try to model the air temperature, the 2-meter air temperature, which is sort of the standard thing. But what we measure isn't that. So the satellites measure something completely different, which has to do with the surface layer. The data from the ships we used were actual thermometer readings, so that's a bit closer. And of course, the weather stations is supposedly closest to what we're actually trying to estimate. So this is the result from the reconstruction we ended up doing from January 1990, which is a period where we apparently had quite a lot of data. We have some blank spots where we don't want to show you the results because we don't trust them, and for good reasons, to do with lack of data and also possibly some numerical issues with the estimation. So this is part of the problem, that we don't have a lot of data all the time. The total amount of data is a couple of terabytes, but that doesn't mean that we have a lot of data about each location at each time. So if you go back to 1880, there's almost no data. You can hardly see that there is data. When you go to 2005, there's a lot more. And that's the satellite data that you can extract, which isn't sort of impaired by cloud issues and so on. And then in between, we have various amounts of data. So we have a lot of data and a lot of space and time to model. And the process that we're looking at lives on different scales. So we heard a bit about different scales before lunch. But here, it's specifically, we have seasonal effects. So we have a spatial field that varies each year in roughly the same way, that repeats. We have a slow climate process, which is basically how this cycle changes slowly over time. And we have things that live sort of in between things that are not quite systematic changes over time, but just things that have long correlation length in time. Long meaning more than a week. And we have the daily scale on top of that. And the total size of the model, once you go to quarter-degree resolution and 60,000 days since 1850, that's 10 to the 11 unknowns. So the Gaussian markov random field models that were briefly mentioned before, we tend to say that you can do about 1 million nodes there. It's sort of the useful practical limit of how many nodes you can have in your model and do the solve for. So this is 100,000 times bigger than that. So if we didn't have any correlation between each day, we'd just do each day over and over again, and that's part of the actual solution. but we need to connect it to the slowly varying processes so that when we go back in time when we have very little data, but we still want to know about climate change, then we need to use the information from other time points to inform us about the actual structure of this. So that ends up giving us a big hierarchical model where each node has a big Gaussian process in it. We will then use the trick of taking stochastic PDEs, where we know sort of what the spectrum is, and to some degree we know what the covariances are, but we can also directly construct Gaussian Markov random field models that approximate those solutions. And that means that we can use the sparse matrices resulting from the Gaussian Markov random fields, but to use that to solve for these Gaussian processes problems. And what we also want to do is to propagate the uncertainty from the, or from everything basically. We have dependent structure parameters that are unknown. We have the processes themselves that have unknown correlation lengths. That also depends on where you are. And to some degree when you are. They might be different for different seasons. And then the observations, we can have quite a complex uncertainty structure and bias that we need to model. So on top of the thing that we actually want to model, we end up having to model lots of other things as well, just to be able to propagate the uncertainty about it into the end product. So what we want is the best estimate we can come up with. We want also a collection of samples, because that's the easiest way to present the total uncertainty about the problem. And it would also be nice to, for each point in space and time, have a better estimate of the uncertainty than you get from a small Monte Carlo sample, because producing that sample is really expensive, so you can't have that many elements in it. So the idea that we developed was to link to a version of a sort of a dampened heat equation. And you can interpret this model in several ways. One of them is as an iterated heat equation, where you first take a heat equation driven by spatially dependent noise, and that's our surrogate for all the driving forces on the climate, so effects of greenhouse gases and so on and so forth. And then you drive another heat equation with that. So we're not trying to directly represent actual physics. We're just trying to come up with a model that can mimic the kind of statistical structures we can see there, by being flexible enough to do what we want. In particular, we want to allow these kappa parameters, which basically controls the local range of the process in space. We want to be able to let that depend on where we are, because it's definitely different over ocean and over land, but it's also different if you're close to the poles or close to the equator. And the nice thing is that you can take that and turn it into this, which is just a multivariate Gaussian. It's a very large multivariate Gaussian, but it's still a multivariate Gaussian. We have a precision matrix Q, and the Markov property just means that you have a zero whenever you have conditional independence between two nodes. That doesn't mean that you have independence, just conditional independence. So if you have 2 points here, and you're conditioning on what happened in between, then the behavior is independent. But you can still have strong dependence over large distances even with this. You might run into numerical issues with the condition number of your matrix when that happens, but that's mostly a problem for the prior distribution of a model like this. Once you start conditioning on data, you tend to break that structure down. So adding something small to the diagonal that we heard about before, once you add data, you add actual values that are large to the diagonal. So it's much safer than that issue. And we can do this by taking sets of basis functions. So we make a specific choice of basis function here, which is local. So here we simplify it as much as we can, so it's piecewise linear basis functions on triangles. So we're basically doing a classical finite element approximation to the whole thing. And that allows us to write down this basis expansion of product of spatial and temporal basis functions and stochastic weights on top of that, where the weights have a multivariate Gaussian structure, where the precision matrix that comes out of this turns out to have this nice sum of Kronecker product structure. So it's not a Kronecker product only, but it's a sum of Kronecker products. And it's on the precision scale, not on the covariance scale. So it's the way things behave on the precision side is not quite the way we're used to from the covariances. And then this is the hierarchical structure, or part of the hierarchical structure. So we have the observations in the middle here, and I'll talk more about these epsilon nodes here, which are related to the observation errors. But we have the observations, and you can either look at the daily means, so that's on the left-hand side here. So then we have the daily scale, but the daily scale conditionally on a slowly moving climate can be sort of written in a hierarchical fashion. And if you then know the seasonal pattern, that tells you sort of a useful conditional expectation for the climate scale and so on. So we build it up hierarchically like that. You can also have covariates like elevation. If it's cold on top of the mountain, we want to capture that in an easy way. So that also comes in here. You can ignore that arrow for now, or throughout the talk actually. And on the right-hand side, we have the daily range in temperatures, the difference between maximum and minimum. And in the results I will show you later, we only looked at the left-hand side, but most of the talk will be about the right-hand side, because it's the same thing as the left-hand side, but worse. So we have these conditional specifications where the daily means are, in the simplest version, they are linear Gaussian connected things. But the range, we know something about range, that it has to be positive, or at least non-negative. You can't have a maximum that's smaller than a minimum. And if you're lucky, you can still model it through Gaussian. If you're far away enough from zero and it's symmetric enough, it turns out when you're looking at the data, no, it's not, you can't. So you have to do something else. And what we're doing here is a transformation model that says that the daily scale is where you see these non-Gaussian behavior. And the long-term things is just a change in that distribution by a scaling factor. So taking a closer look at the observations is that each satellite has its own problems, basically. Partly because of the satellite itself and partly because of what it is measuring on the ground. Is it measuring over ice? Is it measuring over land? Is it measuring over ocean? Because you get a calibration model for each of those that tries to convert those measurements into air temperatures. So in an ideal statistical modeling world, we would build in all of that in one big model and estimate everything at once, and that would be terrible. Because these things are quite complicated as they are, and we really want to be able to take these sort of pseudo temperatures and validate those models independently of the rest, so we know that if there's a problem with the data source, it's easier to detect it if we don't just build it into the full model and hope for the best. So we have detected some issues that way. But you then have to describe the uncertainty about these pseudo observations that you create. And to get it in a coherent framework, we have three ways of specifying these uncertainties. We have one, independent errors, which are basically sort of measurement noise in a sense. We have spatially correlated and possibly temporally correlated errors, and those are the most annoying ones because those are the ones that are hardest to get rid of in the model. We ended up having to have them explicitly as latent unobserved fields that we estimate together with everything else. And those arise because of mostly issues where the error is correlated with the truth. So ideally, we would model the dependence on the truth in this error, but that relationship is non-trivial. So at least having it there as these unknown fields that have spatial structure helps. And then we have systematic errors, like the whole field is shifted up and down by some unknown constant, or possibly some unknown function over space. And then you add those up. So that's our unified framework for dealing with the satellite data. Then we have station data, and those are annoying in a different way. Is that they don't move, and they're always in the same place, which is good compared to ships, for example, which tend to move around, so it's a bit hard to tell what they're doing. But the stations, they have issues where, let's say, the average value, the expected value of the observation, so the bias changes due to reasons that has nothing to do with the climate that you're trying to estimate, the change in. For example, I think it was in Stockholm, where people went and had a look at the information about the station and saw that, well, there was this step change in this temperature series, and they found out that someone had painted the wall of the house. Not sure if it was from black to white or white to black, but it was something of that type. And then, of course, it affects the surrounding area, so there was a change in temperature. And I think the same station, there was someone who had knocked the scale out of alignment with a thermometer, and then someone noticed and fixed it, but didn't say that they did. But you can notice in the series that they had done something like that. So there's all these sorts of things. So what there are methods for is to detect these things. But then you want to estimate how much should you correct this series. And then there are methods for looking at neighboring stations, which then, of course, also have these problems, but hopefully they didn't change at the same time, so you can do relative corrections to the neighbors. But how do you then propagate that uncertainty into our full model? It turns out the easiest way to do that is to not correct the temperatures in the first place, but keep the data as they are, but remember the information about where we think there are changes. And then building this up as a random effects model, where each bias correction is a random effect, which might have a temporal structure even, depending on, I think there was a recent paper that showed that in different countries, these changes behaved either as independent moves up and down, and in other countries, there was more like there was a change compared to the most recent part of the series. So you have a random walk or independent changes, and that depends on how the measurement system has been set up. So there's lots of work one can do just with that model. But given that we build it up like that, we then have the issue of what do we observe? Well, if you have an observation that's meant to represent the daily mean temperature at the location, you just add on this whole combined bias term to the actual temperature and some independent noise, and that's your observation. But if you're observing the maximum or minimum in a location, then you're observing the sum of the daily mean temperature and half of the range, if we define mean as the average of max and minimum, which we did. So then you end up with something like this, where you here have a multiplicative bias instead, because that's sort of a reasonable simplification. So you then get this nonlinear effect of your random terms in the bias correction. But it's a very mild nonlinearity. So that's how we link the observations to the true fields, so to speak, as defined by our model. And this is data from one of the stations. So this is the daily mean temperature, and this is the daily range for a period from early 1950s to the late 1960s. So we see that there's a clear seasonal effect in both of these, and it's a bit hard to see there. It's probably easier to see here that you also have a seasonal effect in the variability. So it's not enough to just model the mean. You have to model the variability for these things as well as a function of time, at least the season. So if you just sample from the different scales of our model, it might look like this. You have the daily contribution, you have the medium-term version, you have the climate signal, and then you have the seasonal pattern. And this, of course, would then be for every point on the globe. If you then feed it into that hierarchical structure I showed earlier, it will look something like this. We have our model daily means and our model daily ranges. And the text dropped, oh, there's the text dropped off. There was no data was harmed when making this figure, but it still looks pretty close to that in spirit, despite the fact that I did not estimate any parameters to do that. That was just quick hand tuning, just to see how easy is it to get something that looks reasonably close to actual data, and it turns out to be really easy. And part of the mains effect that means that you can tell the difference between this and this is actually the discretization error, that this is in whole degrees of Fahrenheit. So it looks more jagged because of that. Otherwise, it's quite similar. So how do we make this non-Gaussian thing work? Well, you can do really a copula transformation, but you need a family of distributions that can capture the types of things you see in the data, which is quite a lot. So we come up with this model, which is on the right-hand side, it's a generalized Pareto distribution, and on the left-hand side, it's also a generalized Pareto distribution. And how do you blend between the two? Well, the easiest way to do that is to blend them as quantiles. So instead of trying to blend the density functions with some conditions or the CDF, then you take the quantile functions instead, and then you just basically add them up, and you get this nice model where you can control the behavior of both tails independently. Because, of course, we know that it's finite on the left. It should start at 0, probably. And on the upper tail, we don't really know exactly what it should look like. It should probably be finite-tailed, because you can't suddenly have 1,000 degrees warm. It can be hot, yes, but not arbitrarily hot. Something that's probably lighter than a Gaussian tail, and that turns out to be what mostly comes out of the estimation as well. So if we're looking at some stations, we have the histogram and 3 different models. So here is a log normal distribution, a gamma distribution, and then this special power quantile model. And we see that the log normal has some problems for that station. It's unclear for that one. The gamma here works okay, but if we take 2 other stations, it might look like this. So this one first is interesting because it's finite on the left, but it's skewed to the opposite direction to what a positive distribution would normally be skewed towards. You would usually have a long tail to the right. But here we have the sort of the heavy tail is to the left, even though it's finite. So none of the usual positive models do that at all. Whereas this one, we have full control over the left and the right tail, so we can do whatever we want. And then we look at this one, which is bimodal, where our model says, sure, why not? This indicates that we have to be careful. We have a model with so many parameters that we can do basically anything. So here, what probably happened is that we have some of these bias corrections that we haven't done yet here. This is on the raw data for a given month. So that bimodality is probably just an artifact of bias, of time-changing bias. So once we feed this through the model, we would expect this to look different, but at least our model says that, okay, so if you really insist, then it will go along and accept it. So if we feed this in and estimate the mean and standard deviation, it's basically spread of the distributions for the daily means and for the daily ranges. So here you see that it's warm at the equator and cold at the poles. We know that. The range is more interesting. It shows that we have this large range in the desert, basically, and small range in other places. This is in February. what's also interesting is the clear pattern that has a very strong opinion about what happens over the ocean, despite the fact that this trial run of things did not use any data over the oceans whatsoever, only land data. And the oceanographers say that, yeah, well, the range is even smaller than this in reality. So here it's estimated to be around 5, but they say it should be sort of 2 or 3 maybe. But considering that it didn't use any data at all, that's quite remarkable, and it's partly because you have data close to the coast that says that, no, it should be going down here. And this tells you what the variability in the range is from day to day, or from year to year even. So here again, you see these patterns, and I don't have the video with me here, but otherwise you will see how these patterns change seasonally as well, so you can see the spring arriving in terms of how variable things are in both of these. And the same thing happens when you're looking at the estimates of the tail shapes of these distributions. This is all very promising. Unfortunately, this did not make it into the final product. So this is an example of the things that we've done a lot of work on and will continue doing work on, but it's not in any actual data product yet. But the idea for doing the computations with this is essentially the same one that is used in the so-called INLA method, the integrated nested Laplace approximations, except that we skip most of it because it would just be too expensive. So we basically do an approximate Gaussian posterior from our whole model. So here we have these slightly nonlinear observations from linear combinations of values. So the linear combinations comes from adding up the basis functions with the weights and then transforming it with these nonlinear things. And if you write down a Newton optimization to find the posterior mode of that for given covariance parameters, then you end up with this, where the precision matrix is just the sum of the prior position and a sparse matrix times the observation precision times that sparse matrix again. If you had linear observations, so if you didn't have this function H, then this Jacobian J would be equal to the matrix A, and you would have A transpose Q A there. And that turns out to be the actual posterior position for a Gaussian when you're conditioning on Gaussian data. And similarly for this one, the update for the conditional expectation or the conditional mode, some of these terms would cancel out, and you would have something basically looking mostly like this. So you would have, or possibly even like that. But the key is that you need to make a linear solve with this approximate posterior precision matrix. And if you remember the beginning of the talk, that is a 10 to the 11 by 10 to the 11 matrix. So you can't have that matrix, ever. What we can have are small parts of it. And we know a lot about the structure of that matrix with its sums of Kronecker products in space and time, etc. And the thing that really breaks it is the data. Because there is no nice structure in the data. The data comes whenever and wherever it is. So we can't use many of the simplifications. Like if you have data on a perfect lattice, you can usually use Fourier inversion, and that's excellent. Here, none of that really works. So we have to be more clever. So this is the bit that takes care of the nonlinearity there, because it's a very nice, simple nonlinearity that only appears in the observation equation. So that's nice. So the problem then turns out, how do we do these linear solves with this big matrix? And by using all the methods we can find is the answer. So first of all, we need a line search for the Newton optimization, because here we have sort of the predictor space that our nonlinear function ends up with. So if you start in a point and the actual optimum should be there, but one step of Newton takes us out here, then that simply means that this is a linear approximation of a model, but this is the nonlinear truth. But then we can take a shorter step along that and start again from there, and that takes us to the finish line much faster in a robust way. And you can do various variants of More importantly, almost, is that even if you can do an approximate solve, or you can do local solves, which would be sort of conditionally exact, and if you then can figure out how to handle all these different scales to get an approximate solve, and often statisticians stop at that point. You just do sort of a sequence of things and then you stop. But if you delve into sort of numerics and all that, we know that, well, if you have this approximate inverse, we can use that in an iterative solver that accelerates the convergence. So we can use the precondition conjugate gradient method, for example, which uses these approximate solves and then finds better search directions to find a better approximation. And once we've done that, we can use the same technique for producing these samples from the model, where we just need to set the right-hand side instead to something to do with data. It's something to do with the location of data and the distribution of data, but not the actual values themselves so much, in a way that if we could compute the Cholesky factor of Q, that's what we would use, and this is sometimes called a least squares simulation. But we can't have Q, and we can't have the Cholesky factor. What we can have is a matrix, a rectangular matrix L, such that L transpose is Q. So it's not the actual Cholesky factor, it's sort of a pseudo-Cholesky factor that fulfills that product. And then, because of all the structure in this, we can apply that rectangular matrix to a vector of random numbers. And that constructs the correct right-hand side for this, of the Gaussian approximation of the problem. So that's a nice little trick we can use. And then comes the problem of how do we do these local approximate solves. So first of all, we have choices of resolution here. So this is an icosahedron that keeps getting subdivided into smaller and smaller pieces. This is not the actual one we used in the project. That's slightly different, because this one keeps points along latitudes. But if you can keep going 3 steps more, then you get down to quarter-degree resolution. So that's about 500,000 nodes in that mesh. But you can do simultaneous solves with sort of a 500,000 nodes. So you can do, if you just did one field one day, you could do the full solve. And with the parallel solvers and so on, I think that was pushed here up into almost 2 million, so that you could do the field and some of these bias fields at the same time. But if you have space-time dependence, you don't want to just run each state independently, because then you will have a very bad approximation in terms of the connection to the neighboring days. So the idea here was instead to build space-time blocks that are small enough. So those would be about this big, about the size of 6 triangles there, and then you would have about 20 or 30 time points for that little region, and then you make them overlap in both space and time, and you then run all of those and combine the results, and that then gives you your approximate solution. And that can also be used to get these slightly better uncertainties than you get from just the samples, because you can compute the exact conditional variances locally. So there's something called the Takahashi recursions, which means that you can take a sparse precision matrix, and then for all the elements of Q that are non-zero, you can compute the elements of the inverse of that matrix without having to compute the rest of the inverse. So if you have a sparse matrix, you get basically this sparse inverse that only have this is partial inverse. And it turns out that if you want the variance of a linear combination of elements that are close to each other, so they're neighbors in the Markov structure, then those are exactly the elements you need to compute that variance. So you can compute the conditional variance in a subregion, and then a conditional expectation. So you turn things into, instead of taking the empirical sum of squares, you're taking the empirical sum of squares of differences between the conditional expectation and the actual expectation. So that reduces your Monte Carlo error in the estimation of the variance. Yes? So, well, I already said that you can basically, you blend these blocks together when you're doing the solve. And then to handle the different scales, we found that essentially the best method would probably do a kind of multi-grid method, or at least approximate multiscale Shor complements, which means that you solve the fine scale only, you propagate the information down to the coarser scales, solve there, and then you propagate the information back again to the fine scale, and that gives you a very nice approximation that takes all the dependence into account. The problem with that is that since we can't have the matrices stored, we need to construct them locally on the fly, means that we have to read the data again, or at least the information about where the data is. And that's expensive. So not doing these clever things with Shor complements, but actually doing separate block solves or conditional block solves was easier to implement and cheaper to run. The trade-off, whether that will be faster in the end because you have to run more iterations, we don't know yet. So this is what we ended up implementing, was that we collect the climatology parts and the covariates in one block. We have these large-scale processes and station biases in one block, and we have the daily scale in one, which includes the satellite bias fields. And then you update one block conditionally on the others. So this is a very traditional block update method. And we know that there are problems with this with convergence. But there wasn't simply enough time to combine this with the conjugate gradient, etc., and all of that. But then you end up with fields like this, where you have the daily scale, you have the slow variance scale, and the climate, and then you add them up into this. And you get the error. So here you have the, let's see, the red line, I think, is based on a few well-controlled stations, and the black line and the gray error bars is our estimate of the same temperatures. So we see that they match up pretty well for this station, or for this location. Here we have some satellite bias estimates for the location. And here we have then an attempt of illustrating the ensemble output. So we have multiple contour curves here, one for each ensemble member. I'm not sure this is the best way to plot these things, but it's a way to plot these things. So you can see where all the samples agree and where they disagree, and here we see that they disagree more over the ocean than over land, and that's simply because, well, we didn't have as much data out there. So you have the data mostly over land here and along some shipping routes, but otherwise you're more uncertain, and that shows up in the ensemble. Similarly, if I think this was a specific heat wave in Australia in 2006, which we specifically looked at as well. So again, we see that over the ocean we have less information, but over land there is more clarity about the structure. So I've sort of talked about some of the issues we dealt with, and some of them I glossed over or didn't mention at all. So one thing that is clear, and that is also part of the thing we see in the output, that is, if we ran more iterations of the algorithm, some strange artifacts kept getting smaller and smaller, which indicates that, yeah, we haven't really converged yet for those bits. So having a method that accelerates the convergence for those hard-to-catch bits in the block structure would be nice. We also looked at non-stationary parameter estimation, because all these parameters depend on where you are, and we need to estimate it. So we looked at having local estimates of the SPD parameters and then blending them together into a joint SPD, which you can then solve in any way you want. So that idea, I think, is definitely sort of the future for these types of models. Because if you want to do it realistically, you should not have a stationary Gaussian process, and you need ways of estimating these things. And the more non-stationary it is, the less interesting it is to do a joint global estimate of those local parameters. The data at the South Pole doesn't really tell us anything about the correlation range in the UK, for example. So why should we care about the global likelihood? As long as we can keep track of the uncertainty. So I'll stop there. Thank you.